Good afternoon, everyone. This is Lawakush Misra from IIMT Group of Colleges Greater Noida. Today, I am here for delivering a lecture on design of keys. First of all, I would like to tell you something about myself. I am working in IIMT College since last 4 years as a assistant professor in the Department of Mechanical Engineering. First of all, you should know what is key. Key is a piece of mild steel which is inserted between the shaft and hub of the pulley to connect these together in order to prevent relative motion between them. It is always inserted parallel to the axis of the shaft. Keys are used as temporary fastening and are subjected to crushing and shearing stresses. A keyway is a slot or recess in the shaft and hub of the pulley to accommodate a key. Now we will go through types of keys. There are following types of keys such as first one is the Sankhi, second one is the saddle key, third one is the tangent key, fourth one is the round key, and last one is the splines. First one is the Sankhi. What now you should know what is Sankhi. The sunk keys are provided half in the keyway of the shaft and half in the keyway of the hub of the pulley. Now we will go through different types of sunk keys. First one is the rectangular sunk key. The usual proportions of this key are as first of all width of the key, which is denoted by small w, and it is equal to d by 4, and thickness of key, which is denoted by t, that is equal to 2 into w by 3. When we will put here w equal to d by 4, then after simplification we will get here finally t equal to d by 6, where d is the diameter of the shaft or diameter of the hole in the hub. The key has taper 1 in 100 on the top side only. We can say this taper as a 1:100. Now a figure of rectangular Sankhi is showing on the screen. See here, this is the shaft having diameter small d. This is the side view of the shaft along with assembly of the key. This is the particular key, and this is the front view after assembly of shaft and key. This taper is 1:100, and this is the diameter of the shaft. In side view, you can see here W. W is the width of the key, and T is the thickness of the key. In side view, the key will be seen in this form, just like you can say like a small rectangle. Second one is the square Sankhi. The only difference between a rectangular Sankhi and a square Sankhi is that its width and thickness are equal. As the name is square, so width and thickness will be equal. So we can say that W equal to T. W is the width of the Sankhi and T is the thickness of the Sankhi. So in the case of square Sankhi, W will be equal to T, and finally it will be equal to D by 4. Third one is the parallel Sankhi. The parallel Sankhis may be of rectangular or square cross section, uniform in width and thickness throughout. It may be noted that a parallel key is a taperless and is used where the pulley, gear, or other mating piece is required to slide along the shaft. Next one is the jib head key. It is a rectangular sunk key with a head at one end known as jib head. It is usually provided to facilitate a removal of key, a jib head key, and its use in shown in the figure. See here, this is the figure for the jib head key. This is the taper portion. It is also same as 1:100. This is inclined at angle of 45 degree. The thickness of T is here as small t and width is as small w. This portion is 1 t and this portion is 1.75 t. It means that if you have small t, that is the thickness of the Gibratt key, then you can find out the most of the portion of this key. This one is the assembly with the soft jib head and the pulley. The usual proportion of the jib head key are as width, which is denoted by small w, that is equal to small d by 4, and thickness at large end, that will be small t equal to 2 into w by 3, and finally after simplification it will be small d by 6. Next one is the feather key. A key attached to one member of a pair and which permits relative axial movement is known as feather key. It is a special type of parallel key which transmits a turning moment and also permits axial movement. It is fastened either to the shaft or hub. This diagram is showing the arrangement of the feather key along with the set screw as well as uh, soft and pulley. Next one is the Woodruff key. The Woodruff key is an easily adjustable key. This is a piece from a cylindrical disc having segmental cross section in front view as shown in the figure. A Woodruff key is capable of tilting in a recess in the shaft having the same curvature as the disc from which the key is made. This key is largely used in machine tool and automobile construction. Here, this figure is showing the arrangement of the Woodruff key. This one is the front view and this one is the side view. Now we will go on second number. So far, I was discussing about the Sankhi. Now, second one is the saddle key. The saddle keys are of the following two types. First one is the flat saddle key, and second one is the hollow saddle key. First, flat saddle key. A flat saddle key is a taper key which fits in a keyway in the hub and is flat on the shaft as shown in the figure. This is the figure for flat saddle key as well as hollow saddle key. Now we will discuss about the hollow saddle key. A hollow saddle key is a taper key which fits in a keyway in the hub and the bottom of the key is shaped to fit the curved surface of the shaft. Since saddle keys hold on by friction, therefore these keys are suitable for light loads. In this figure, flat saddle key as well as hollow saddle key are shown, and here the circle is showing the diameter of the shaft, and this one is the flat saddle key where W is the width of the flat saddle key and small t is the thickness of the flat saddle key. And second one is the hollow saddle key. In this diagram, same as first one. Here small w is the width of the hollow saddle key and small t is the thickness of the hollow saddle key. This is the formula which is used for the saddle keys. Small t equal to w by 3, where w is the width of the key, and finally when we will put here the value of w as earlier discussed, Then finally we will get small t equal to small d by 12. Now third one is the tangent keys. The tangent keys are fitted in pair as shown in the figure below. Each key is to withstand torsion in one direction only. These are used in large heavy duty shaft. See here, this is the arrangement of tangent key. This circle is showing the diameter of the shaft, and tangent key is fitted here just at a uh, circumference of the uh, shaft, and it is just fitted here in the as it in the form of tangent. Fourth one is the round key. These keys, as shown in the figure, are circular in section and fit into holes drilled partly in the shaft and partly in the hub. They have the advantage that their keyways may be drilled and reamed after the mating parts have been assembled. Round keys are usually considered to be most appropriate for low power drives. In this figure, arrangement of round key as well as uh, uh, here arrangement of round keys are shown, and this occur in the when it is assembled with the shaft, then there is a requirement of a tapered pin for the tight fitting of it. Now we will go through the forces which are acting on a Sankhi. When a particular key be in the action along with shaft and pulley, then different forces acts on the key. Now we will go through forces acting on a Sankhi. When a key is used in transmitting torque from a shaft to a rotor or hub, the following two types of forces acts on the key. First one is the first force, which is denoted by F1. I will show it in the figure further. This force F1 induced due to fit of the key in its keyway, as in a tight fitting straight key or in a tapered key driven in place. These forces produce compressive stresses in the key which are difficult to determine in magnitude. Second force which acting on the Sankhi, that one is denoted by F. It occurs due to torque transmitted in the shaft. These forces produce shearing and compressive or crushing stresses in the key. The distribution of the forces along the length of the key is not uniform because the forces are concentrated near the torque input end. The non-uniform of distribution, the non-uniformity of distribution is caused by the twisting of the shaft within the hub. In design a key, forces due to fit of the key are neglected, and it is assumed that the distribution of forces along the length of the key is uniform. See here in this diagram, forces acting on Sankhi are shown. This one is the shaft having diameter small d, and this dotted portion having some curve at this end. This is the keyway. I will discuss further on about what is keyway. And in this keyway, a Sankhi having length small l is inserted here. This diagram is showing the arrangement of shaft and key in the side view form. When key is fitted with the soft. After then, when the when we start machine, then it rotate at a very high speed. Here, this is showing the rotation of the soft. Here, this is the key which is showing having the different forces. First, we will discuss about the dimension of the key. From here to here, which is denoted by small w, this is the width of the key, and from here to here, this is denoted by small t. This is the thickness of the key. As I discussed earlier, two forces acting on the key when it is under the action. First force is F1 and second force is F2. And these two forces act in this fashion. Now, strength of a Sankhi. A key connecting the soft and hub is shown in figure which was discussed on the last page. Let capital T is torque transmitted by the soft. Capital F, tangential force acting at the circumference of the soft. Small d, diameter of the soft. Small l, length of the key. Small w, width of the key. Small t is thickness of the key, and sigma c equal to shear and crushing stresses for the material of the key. It is very important to know that sigma c is the shear and crushing stresses for the material of the key. Means for that particular material of which the key is manufactured. A latest consideration will show that due to the power transmitted by the soft, the key may fail due to shearing or crushing. When the power is transmitted, the particular key may fail due to shearing or crushing. Considering the case of shearing, considering shearing of the key, the tangential shearing force acting at the circumference of the shaft, which is denoted by capital F, equal to area resisting shearing into shear stress. This will be finally equal to L into W. This L into W is showing the area resisting shearing, and tau is the shearing stress. Therefore, torque transmitted by the shaft, that is torque capital T equal to F into D by 2. When we will put here the value of capital F as L into W into tau, then finally we will get capital T equal to L into W into tau into D by 2. We will take it as a equation number 1. Considering crushing of the key, now we will consider about the crushing of the key. The tangential crushing force acting at the circumference of the shaft, which is denoted by capital F, equal to area resisting crushing into crushing stress. Now, area resisting crushing will be L into small t by 2 into crushing stress sigma c. Therefore, torque transmitted by the shaft, that is capital T, equal to F into D by 2. Now we will put here the value of capital F as L into T by 2 into sigma c, and D by 2 will be multiplied with it. Then finally we will get T equal to L into T by 2 into sigma c into D by 2. This is as a equation number 2. Now the key is equally strong in shearing and crushing. If we will assume here the key is equally strong in the crushing and shearing. For that thing, there is a particular condition. The torque transmitted in both the cases should be equal. Now we will equalize the equation number 1 and 2. From equation number 1, L into W into tau into D by 2 equal to, from equation number 2, L into T by 2 into sigma c into small d by 2. After simplification, we will get here W by small w by small t equal to sigma c by 2 into tau. This is equation number 3. The permissible crushing stress for the usual key material is at least twice the permissible shearing stress. Therefore, from equation number 3, we have small w equal to small t. In other words, a square key is equally strong in shearing and crushing. It means that when we will put here small w equal to small t, then we will get sigma c equal to 2 into tau. In order to find the length of the key to transmit full power on the shaft, the shearing strength of the key is equal to the torsional shear strength of the shaft. We know that the shearing strength of the key, that is denoted by capital T, equal to small l into small w into tau into small d by 2. Let it equation number 4. And torsional shear strength of the shaft, which is denoted by capital T, equal to pi by 16 into tau 1 into dq. Let it equation number 5. Taking tau 1 as shearing stress for the shaft material, now from equation number 4 and 5, we have, see here, we will equalize the equation number 4 and 5. Then we will get L into W into tau into d by 2 equal to pi by 16 into tau 1 into dq. Now we will simplify it, and we put here some values, and finally after simplification we will get here L equal to 1.571 d into tau 1 by tau. When the key material is same as that of the shaft, in that case tau 1 will be equal to tau. Now finally from equation number 6, when we will put here tau 1 equal to tau, then we will get finally L equal to 1.571 into small d. Now we will consider a numerical, because since this topic is related to numerical, so it is, the lecture will be incomplete without the discussion of the numerical. See here a question. A 45 millimeter diameter shaft is made of steel and a 45 millimeter diameter shaft is made of steel with a yield strength of 400 megapascal. A parallel key of size 14 millimeter wide and 9 millimeter thick made of steel with a yield strength of 340 megapascal is to be used. Find the required length of key if the shaft is loaded to transmit the maximum permissible torque. Use maximum shear stress theory and assume a factor of safety of 2. According to question, first we will see what is given. According to question, a 45 millimeter diameter shaft, which is made of mild steel. It means that diameter of the shaft, which is denoted by small d, is given equal to 45 millimeter, and sigma yt for the shaft, that is the yield strength of 400 megapascal. It is for the steel, that is the sigma yt for the shaft, which is made of steel. That one is the equal to 400 megapascal. Now megapascal will be converted in the Newton per millimeter square. The reason behind it, diameter of the shaft is given in the millimeter, so we will try. First thing, we will put the dimension of all the portion in a uniform unit. So we will convert it in the Newton per millimeter square. Here width is given as a 14 millimeter and thickness is given as a 9 millimeter, and sigma yt for key, as it is given in the question that yield strength of 340 megapascal, sigma yt for the key material, that is 340 megapascal. Now we will convert megapascal into Newton per millimeter square, and we also have Fs, means factor of safety, equal to 2. Now on the basis of given data, we will think which particular formula will be used here. Actually क्या है, actually for obtaining any particular dimension or any particular thing, we can use different formula, but on the basis of given data, we will consider a particular formula, and on the basis of that formula we will find the required values. Let L is the length of the key, which is not given, so we will assume it. According to maximum shear stress theory, the maximum shear stress for the soft, as per the question, we have to use maximum shear stress theory, and we have to use maximum shear stress theory. So, according to the maximum shear stress theory, the maximum shear stress for the soft, that is tau max equal to sigma yt divided by 2 into Fs. So sigma yt is given as a 400 Newton per millimeter square will be put here, and 2 into factor of safety is also given as a 2. After simplification, we will get tau max equal to 100 Newton per millimeter square, and maximum shear stress for the key, that is the tau k equal to sigma yt divided by 2 into Fs. The value of sigma yt is given as 340 Newton per millimeter square. We will put here divided by 2 into 2. 2 is the factor of safety. After simplification, we will get 85 Newton per millimeter square. We know that the maximum torque transmitted by the soft and key, that is capital T equal to pi by 16 into tau max into d cube. Here we will put the value of tau max, which we have calculated here. Then pi by 16 into 100 into diameter of the soft is already given as a 45 millimeter. We will put here, that will be into d cube. After simplification, we will get here 1.8 into 10 power 6 Newton millimeter. This is the value of the maximum torque transmitted by the soft and key. First of all, let us consider the failure of key due to shearing. We know that the maximum torque transmitted, that is the capital T, we just calculated here. Capital T equal to L into small w into tau k into d by 2. We will put here the value of capital T as a 1.8 into 10 power 6 into L. We have assumed as a length of the key, into we will put the value of W as a 14 millimeter, and tau k we have calculated earlier as a 85 Newton per millimeter square. We will put here into the value of diameter of the soft as 45 millimeter. We will put here divided by 2. Just after simplification, we will have 26775 into L. It means we have 1.8 into 10 power 6 equal to 26775 into L. Now we will finally find the value of L, that is the length of the key, equal to 67.2 millimeter. Now considering the failure of the key due to crushing, we know that the maximum torque transmitted by the soft and key, that is denoted by capital T, equal to L into T by 2 into sigma ck into d by 2. Now we will put here the value of capital T, and we will put here the value of all the other things. After simplification, finally we will get the value of L as a 104.6 millimeter. See here, once we obtain the value of L as a 67.2 millimeter, and after then again we find the value of 104.6 millimeter. Since we are doing the design here. In the case of design, we will consider the larger value. So we will take the larger of these two values. So finally, we will take L equal to 104.6. We can take it in the round figure as a 105 millimeter. This is the answer. Now we will go through the effect of keyway. Since we discussed earlier that uh, keyway, which is used 2-3 times, so we should know what is the keyway and what is the effect of keyway. First of all, you should know what is keyway. Keyway is a particular slot which is which occur half in the soft and half in the pulley, and the whole portion is known as a keyway. Now, the keyway is a particular slot in which we insert the key for the tight fitting of the soft and pulley. Now we will see here what is the effect of keyway. The keyway cut into the soft reduces the load carrying capacity of the soft. This is due to the stress concentration near the corners of the keyway and the reduction in the cross-sectional area of the soft. In other words, the torsion strength of the soft is reduced. The following relation for the weakening effect of the keyway is based on the experimental results by H.F. More. This is the formula for the effect of keyway. Small e equal to 1 minus 0.2 into W by D minus 1.1 into H by D, where E is the soft strength factor. It is the ratio of the strength of the soft with keyway to the strength of the same soft without keyway. W is the width of the keyway, D is the diameter of the soft, and H is the depth of the keyway, which is equal to thickness of key, that is the small t divided by 2. Since we have lackness of the time, so I will I would like to finish my lecture here. Uh, thank you for listening.